Good afternoon, class. We are looking at Chapter 9, Systems of Equations and Inequalities, and here's Section 9.5, Matrices and Matrix Operations. So we cover systems of linear equations in 2 variables, in 3 variables, systems of nonlinear equations, partial fractions, and now matrices and matrix operations. The objectives are to find the sum and difference of 2 matrices, find scalar multiple of a matrix, find the product of 2 matrices. So reminding you of what we have done, system of equations, a group of 2 or more equations, they can be solved by graphing, substitution, or addition method. And types of system, a system of 2 linear equations, 2 variables can have 1 solution, no solution, or an infinite number of solutions. An inconsistent system, ultimately, you have 2 lines that are parallel, equal slopes, different y-intercepts. Consistent system with independent equations. 2 lines that have a point of intersection. They have different slopes and 1 unique solution. Consistent system with dependent equations. Ultimately, the 2 equations are identical if you solve for y, which means they have equal slopes, they have equal y-intercepts. Nonlinear system of equations. A nonlinear system of equations is a system of equations in which at least 1 equation is not linear, that is, one whose graph is not a straight line. As you can see here, a parabola and a line, they don't have a point of intersection, no solution. Just 1 point of intersection, 1 solution, 2 points, therefore 2 solutions, 2 points of intersection, so it varies. We went over partial fractions, and here's what it meant. We know how to add irrational functions. The reverse process is called partial fraction decomposition. Any rational function, a ratio of polynomials, can be expressed as a sum of simpler fractions called partial fractions. This process of decomposing a rational fraction into simpler rational expressions that we can add or subtract to get the original rational expression is known as partial decomposition fraction. In other words, if you look at these two, by the way, adding or subtracting, subtraction is a form of addition. You take the common denominator, LCD, the least common denominator, which is x minus 1 times x plus 2. So 2 times x plus 2 minus 1 times x minus 1, and you put them together. And combination is x plus 5 over x squared plus x minus 2. So we know how to go from left to right. Reversing the process, if we have this one and we want to get these two simpler fractions, it's known as partial fractions. And now 9.5, matrices and matrix operation. A matrix is defined as a rectangular array of numbers. So you have a number of rows, row 1, 2, all the way to row n. You have various columns, column 1, column 2, so on and so forth. So the way we call this, if this matrix is A, capital A, this entry is A1, 1. This one is A1, 2. We write the row first, column second, A1J, A1N. The next one would be A21, A22, and you move on. And the last one would be AM1 all the way to AMN. And this is M by N matrix. M by N matrix. M is the number of rows, N is the number of columns. A matrix has rows and columns. The number of rows and columns are used to name the matrix. The plural of matrix is matrices. Here's one example. As you can see, we have a 1 and 2 rows. 1, 2, 3. Let's just put it here. So 1, 2, 1, 2, 3. Therefore, it must be a 2 by 3 matrix. This one has 1, 2, 3 rows. 1, 2, 3, 4 columns. Therefore, it's a 3 by 4 matrix. That's as far as the size and dimensions are concerned. Matrices are classified by their dimension. The number of rows and columns. A matrix with m rows and n columns has dimension m by n. A square matrix has the same number of rows as columns. The dimension of a square matrix is n by n. You could say m by n, but normally we go with n by n. So as we mentioned before, if you look at this one, you have 1 and 2 rows, 1, 2, and 3 columns. This is a 2 by 3 matrix. Determine the following matrices by their dimensions. So matrix A, 1, 2, 3 rows, 1, 2 columns. It's 3 by 2. Matrix B, 1, 2, 3 rows, 1, 2, 3 columns. It's a 3 by 3 matrix. In fact, it's a square matrix because the number of rows and columns are identical. This one has just one row. 1, 2, 3, 4, 5 is the number of columns. So 1 by 5. Sometimes they just call it a row matrix. So it's a row matrix. That's the terminology is used. We also have equivalent to this concept column matrix when we have just one column and a number of rows. Defining equality of matrices. Two matrices are equal if they have identical dimensions such that corresponding elements match exactly. So if one matrix is the A matrix, one matrix is the B matrix, Aij equals Bij. I refers to the number of the row number. J refers to the column number. Given these two matrices, A is 2, 1, PQ, B is X, Y minus 1, 0, find the missing values. Well, the two are equal. So corresponding elements must be identical. This must be identical to this one. Just for the sake of argument, by the way, this is A11, this is B11. So X must be 2 or 2 must be X. This one must be the same as this one. Location for this one is A12. For this one is B12. You write the row first. So Y must be 1. This one must be identical to this one. Location for this one is A21. For this one is B21. These two must be identical. Q must be 0. Location would be A22. For this one, B22. That's pretty straightforward. The sum of two n by n matrices, A and B, is the n by n matrix A plus B in which each element is the sum of the corresponding elements of A and B. In other words, you can only add if you have identical dimensions, number one. Number two, corresponding elements, add them up. So for example, notice this is 2 by 2, so is this one. This is a 2 by 2 matrix. It's a 2 by 2. And if they are not 2 by 2, you can't add them up. So that means 5 will be added to -4. And the rest of them accordingly. -6 and 6, 8 and 8, 9 and -3. So when we do that, this becomes 1, 0, 16, 6. That's how you add them. Graphing calculators are capable of doing that. So the methodology is to first enter the matrix editor. So matrix editor found by pressing second and x to the power of -1. Use the arrow key to the right to edit the dimension you want. First edit dimension. Press enter. Put all the entries using the arrow keys. Press enter. So for example here, okay, when you go to matrix editor, you edit, it's A. The very first thing you do, you change this. For example, you change it to 2 by 2. And we put 5 minus 6, 8, 9, just in the proper spot. For B, we put -4, 6, 8, -3 in the proper spot. And if you go with addition, okay, add the two matrices, you get the result that you got here. Let's add A plus B. If A and B are given as follows, the question is, can we add them up? And the short answer is no. Matrix A and B have different dimensions, therefore the sum does not exist. It's undefined. Why is that? A is 2 by 2, and B is 2 by 3. Can't be done. In order for you to add two matrices, they must have identical dimensions. Zero matrix, additive inverse, A matrix with only zero element is called a zero matrix. Just like a zero element of addition that its number zero is a zero matrix. Every element of that matrix is zero. For example, this one is a 1 by 3 zero matrix. This one is a 2 by 3 zero matrix. Every element is zero. So it's pretty straightforward. The element of matrix minus A are the additive inverses of the elements of matrix A. In other words, whatever matrix A is, each element write the opposite of that. Example 5, find matrix minus A and add them. So if A is a 2 by 3 matrix, first of all, 1, 2, so let's just write it. Always, it's a good practice to write the dimensions, 2 by 3. What is minus A? Minus A, you just change those to the opposite. This becomes positive 5, negative 2, positive 1, negative 3, negative 4, positive 6. So that would be the minus A matrix with the same dimension, namely 2 by 3. I mean, obviously, if you add them up, what happens? They should add up to 0 as you add up numbers. So you are adding the same elements, minus 5 and so forth. And you end up with a 2 by 3 zero matrix. And just as we do with numbers, a plus 0 is 0 plus a is equal to a. This 0 is a zero matrix. A plus minus a is the same as a minus a equal to 0. A plus b is b plus a. You can put them in any order. A plus b plus c is a plus b plus c. Commutative property, associative property. So basically, what you do to numbers, you can do to matrices. The only thing is they must have the same dimensions. Otherwise, you can't add or subtract. Same dimensions. Okay. Matrix subtraction, two matrices with the same dimension can be subtracted as follows. A minus b is a plus minus b. So a simple example, we want to subtract this from this because they both are 2 by 2. This is doable. So you can only do it if we are dealing with the same dimensions. And so you can do it in one shot and say minus 5, for example, minus minus 3, that means plus 3. Minus 5 and plus 3 is minus 2. 6 minus 2 is 4. 2 minus 5 is negative 3. 4 minus minus 8 is plus 8 or 12. Or change it to a plus and change every element to its opposite. So negative 3 becomes positive 3. This is negative 2 minus 5, 8. And now add them up. Either way is fine. It's pretty straightforward. Again, as an example, just add these two and the rest of them. And we end up with the following, of course, 2 by 2 matrix. So we have -5 and 3 is -2, 6 and -2 is 4, 2 and -5 is -3, 4 and 8 is 12. Add A and B are given, and we want to find A plus B and A minus B. And summary of matrix addition and subtraction is that if A and B are both m by n matrices, then the sum of A and B, or A plus B, is a matrix obtained by adding corresponding entries of A and B. The difference of A and B, or A minus B, is obtained by subtracting corresponding entries. It's very straightforward. So we want A plus B, and both of them are 2 by 3, therefore it's doable, and we are going to write both of them. So again, 1 and -3, it's -2, -2 and 0 is -2, 2 and 4 is 6, 0 and 2 is 2, -1 and 1 is 0, 3 and -4 is -1. So that would be A plus B. And all of them, A, B, the resulting sum, they're all 2 by 3 matrices. A minus B. So as an example, this would be 1 minus -3, which means +3, which means 4. -2 is not changing because this is 0. 2 minus 4 is -2. 0 minus 2 is -2. -1, -1 is -2. 3 minus -4, that means +4 is 7. So this is also a 2 by 3 matrix as expected. The product of a scalar, a constant, a number, a real number, and a matrix A is the matrix K times A, each of whose element is K times the corresponding element of A. For example, we want to multiply the matrix by number 5. And by the way, you can have the number in front of a matrix or to the right, makes no difference. It's a product of the number by each element. So 5 times 2 is 10, 5 times -3 is -15, 5 times 0 is 0, 5 times 4 is 20. That's how we write it, and it's pretty straightforward, everybody. So again, just multiply the scalar, or the number, or the constant by each element, and we are done. Matrix multiplication, example 9, find part A 4 times A, B 1/3 times the C, 3A minus 2B. All right, let's start with 4A. So you put this one, and in front of it, put number 4. So you want to multiply each element of the A matrix by 4. So obviously 4 minus 8, 8, 0, minus 4, 12. So that's pretty straightforward, everybody. Now, write the C matrix and put 1/3 in front of it, meaning you are going to multiply each element by 1/3. So when we multiply by 3, we get 1. This one 1/3. This one doesn't change, and this one is negative 4/3. That's what we get. Three A minus 2B. So we write the A with 3 in front of it minus, we write the B with 2 in front of it. So let's see what happens. This one becomes 3 minus 6, 6, 0, negative 3, positive 9. This one, we are going to apply the negative 2 so we can add them up. So this one doesn't change. We are going to say plus, going to distribute the negative 2. So this becomes 4. This becomes minus 6. This becomes minus 2, minus 4, minus 2. And as I said, we are changing this to a plus sign, everybody. So pay attention that this is a plus sign. And so just add them up. 3 and 0 is 3, minus 6 and 4 is negative 2s. These two cancel each other, 0, minus 2, minus 7, plus 7. And that's the final answer. So it's very straightforward, everybody. The addition, subtraction, scalar multiple, it's not a big deal, everybody. We are ready to move on. Now we're going to move on to matrix multiplication. The product of AB and M by N matrix A, so matrix A must be M by N, and N by K matrix B. Notice these two, that means the number of columns for the first matrix, the number of rows for the second matrix must be the same. So the product of AB of an M by N matrix A and N by K matrix B is an M by K. So the number of rows come from the first one, the number of columns comes from the last one, M by K matrix, and is found as follows. So this is extremely important for this to work. Now let's look at the result. To find the ith row, jth column element of AB, multiply each element in the ith row of A by corresponding elements in the jth column of B. The sum of these products give elements of row I, column J of AB. The product AB can be found only if the number of columns of A is the same as the number of rows of B. The final product will have as many rows as A and as many columns as B. That's very important, everybody. So that's the way it's going to work. Let us find RC, the product of a row vector 1 by n matrix and column vector n by 1 matrix. R stands for row, C for column. So the dimension is 1 by 3 here, 3 by 1 here. So the resulting vector would be 1 by 1. Do you see that? 1 by 1. So how do we come up with the answer? 1 times 2, negative 2 times negative 1, 4 times 3. So one more time. 1 times 2, negative 2 times negative 1, 4 times 3. This is 2, this is 2, this is 12. They add up to 16. As a matter of a matrix, we would put it in a matrix format and say 1 by 1. So again, 1 by 1. So if you understand how to do this, then if we have more of them, it works in the same manner. Here's an example. We want to multiply this matrix by this matrix, and the very first thing we are going to do, we are going to write the dimensions. I can't emphasize this enough. Whenever you want to multiply matrices, write their dimensions and the resulting one. So clear, and more importantly, can it be done? So this one has 1 and 2 rows, 1, 2, and 3 columns. So this is 2 by 3. This one has 1, 2, 3 rows and 1 column. So this is 3 by 1. That's the first thing. So can we multiply them? Because these two are identical, yes, we can. So what would be the resulting matrix? The resulting matrix would be 2 by 1. So how do we multiply? So one way is to completely, for now, ignore this one. Imagine this doesn't exist and just deal with this times that. Okay, so let me actually cross it out and I'm going to erase it. So let's say for now, This doesn't exist. How about that? You don't even see that. Okay, I crossed it out. So how do you do the multiplication? You multiply this row by this column. 2 times 12 plus 7 times 18 plus 5 times 9. This is uh, this is 24 plus 7 times 18, 126 plus 45. You add up those three numbers, 24 and 126 is 150 and 45. So they add up to 195. So that would be the first entry, the top. And now we are going to multiply. So the result here, okay, and I'm going to erase that. The result here is 195. And this one we don't know yet. We are going to do it. So never mind the second one. I want to make sure we understand this one. Okay, everybody? Let me erase my work. And now we are going to multiply the second row of the first by this column. So now I'm going to actually get rid of this. So ignore that, don't see it. So what do you get? You get 4 times 12 plus 6 times 18 plus 9 times 9, and it goes here, which is, of course, 4 times 12 is 48 plus 108 plus 81 and this would be 237. Do you see that again? If we are ignoring this one, we are ignoring this one. Okay, so that's how you do the math. Let me erase my work. And so you end up with a 2 by 1 matrix. Notice this has 2 rows, 1 column. This is how you do the multiplication. So a quick recap. The first row by the first column, and that gives you the very first entry, A11. The second row times the column gives you the second entry. Okay, that means A21 in essence. This is A11. That's how you do the multiplication. The multiplication is pretty involved. As long as you can do a couple of them for practice is good enough. If it gets very involved, you can always use a calculator, but you need to understand the process. So we want to multiply these two. So let's write them down. And let's write the dimensions. This one is 1, 2 rows, 1, 2, 3 columns. This is 2 by 3. This one is 1, 2, 3 rows, 2 columns, 3 by 2. Can we multiply? These two must be identical. The answer is yes. So what is the result? The resulting matrix must be a 2 by 2 matrix. So I would write the dimensions first. It is extremely important to know what we are doing. Okay. All right. So let's see what we do. We are going to multiply. So we are going to multiply the first row by the first column, these two. So we get minus 3 times minus 6 plus 4 times 2 plus 2 times 3. That's the very first entry. In fact, ignore that. Assume it doesn't exist. So now you multiply it by the second and you put it here. Minus 3 times 4, 4 times 3, 2 times negative 2, add them up. So you multiply this by this. Minus 3 times 4, 4 times 3, 2 by negative 2. Now, forget about this row. Let's go to the next row. Again, ignore that. Now we are going to deal with this guy with a different color. So 5 times minus 6, 0 times 2, 4 times 3. Now multiplied by this one, 5, and put it here. 5 times 4, 0 times 3, 4 times negative 2. So what happens? Just add them up. 18 and 8 and 6. 32, negative 3 times 4, 4 times 3. They cancel each other. Negative 4, negative 30 and 12, they add up to negative 18 because this is 0. Again, this is 0. 20 minus 8, they add up to 12. And look at the result, which is a 2 by 2 matrix. And we're done. Again, if it gets more complicated, you can always use a calculator, but please understand the process. Now, what if you were using a graphing calculator? You would say the matrix, you first change the dimension to 2 by 3, and you enter those entries, minus 3, 4, 2, 5, 0, 4. And the next one should be 3 by 2, and you put those entries, negative 6, 4, 2, 3, 3, minus 2. And now if you write A times B, it will calculate it for you, and you have the result. So technology can do it, obviously, and it's not that big of a deal. Now, what is important to know, if you recall, in the case of numbers, A times B is the same as B times A. This is not the same. What is B times A is this one, and can we do B times A? First of all, again, remember B is 3 times 2, and this is 2 times 3, okay? And because if you want, let me just write it here so it becomes clear why it can be done. B is 3 times 2, and if you multiply it by A, which is 2 times 3, because these two are identical, yes, it can be done, and the result will be 3 by 3. Okay, so B times A is a 3 by 3 matrix, whereas A times B is a 2 by 2 matrix. Completely different. So AB and BA are not the same. They become the same in some cases, including the times that A and B are inverse matrices and their product is an identity matrix. All right. We want to find A, B, and BA. Row one of A times column one of B, row one of A times column two of B, and so on, if that helps. So first write A and B, then write their dimensions. This is 2 by 3, everybody. 2, 1, 2, 3 by 3. This is 1, 2, 3 by 2, just like the previous page, and their product is 2 by 2. So this is just like before. So for the first one, we are going to multiply these two and add them up. 3 times 2 plus minus 2 times negative 1 plus 1 times negative 3. That would be the first entry, just like previous one. Now I'm going to multiply by the second one. We get 3 times 4 plus minus 2 times 3 plus 1 times 1. Then we are going to multiply this one by this one. We get 0 times 2, 4 times negative 1 times negative 3. And finally, we're going to multiply this one by this one, 0 times 4, 4 times 3, negative 1 times 1. This is how we do that, everybody. Take a look at what we've done. Add them up accordingly. For example, 6 and 2 is 7. My apologies, 8 and minus 3 is 5. 12 minus 6 is 6 and 1 is 7. 0 doesn't do anything. Minus 4 and plus 3 is minus 1. 0 doesn't do anything. 12 minus 1 is 11. And we're done with AB. Let's look at BA. And again, dimensions. This one is 1, 2, just this one. 3 by 2 here, 2 by 3 here. Okay. So the result, because these two are identical, yes, we can multiply B times A. The result should be 3 by 3. The result is a 3 by 3. Okay. And so just as an example, we do some of them. Okay. So we are going to multiply this one by this one. So you get 2 times 3, 4 times 0. You get minus 1 times 3 plus 3 times 0. We are looking at the very first column. And then minus 3 times 3 plus 1 times 0. So take a look at what happens. This one times this one. This one times this one. This one times this one. And the rest of them follow. We're not going to go over everything, but just the next one would be this, and the next one you multiply by this in the following manner, that the next one would be 2 times minus 2, 4 times 4 is the first one. minus 1 times negative 2 plus 3 times 4 is the next one here. And then minus 3 times negative 2, 1 times 4 is the last. Okay. And the last one, you're going to multiply it by this one now. And that would be the last class. That would be the last column. 2 times 1, 4 times negative 1 goes here. So 2 times 1 and 4 times negative 1, they add up to negative 2, for example, the very last one. Minus 1 times 1, 3 times negative 1 is the next one. Negative 3 times 1, 1 times negative 1. For example, right here is minus 3 and this is minus 1 is 4. The very last entry becomes negative 4. So BA, as you can see, AB and BA are two different things. I'm going to leave it for you to fill these two parts. You already have the answers, so you really shouldn't have any problem uh, finishing it off. So, but just to make sure that you're fine with that, okay? It's an application. It's an interesting application. A contractor builds three kinds of houses: Model X, Y, and Z. So Model X, Model Y, Model Z, with the choice of two styles of colonial and ranch. So to understand what's happening, this one we're going to call it A matrix. So Model X has 0 colonial, 30 ranches. Model Y has 10 of those, 20 of those. And Model Z has 20 colonials and 20 ranches. Colonials need 10 units, if you will, of concrete, 2 units of lumber, 0 units of brick, 2 units of shingles. Ranch would need 50 units of concrete, 1 unit of lumber, 20 units of bricks, and 2 units of shingles. We're going to call it the B matrix. So matrix A below shows the number of each kind of house the contractor is planning to build for a new 100 home subdivision. If you add those numbers, 10 and 20, 30 and 30, 60 and 40, we are making 400 home subdivision. There are a total of 100. The amounts are shown in matrix B, okay, while matrix C gives the cost in dollars for each kind of material. So concrete cost per unit is 20 bucks or 20,000, whatever 20 represents, okay? Probably it's just dollars. Lumber is of 180, brick is 60, and shingles is 25. So C gives the cost in dollars for each kind of material. Concrete is measured in cubic yards. Lumber in 1,000 board feet. So 1 unit, that means 1,000 board feet. Brick in 1,000, and shingles in 100 square feet. So these are the information given. What is the total cost of materials for all houses of each model? So we want to see the cost for each model. How much of each of the 4 kinds of material must be ordered, and find the total cost of the materials. Let's see how we use matrices. First, we want to see what is the total cost of materials for all houses of each model. So, and I'm repeating matrix A, matrix B, matrix C, just rewriting what we had in the previous case. So amount of each material needed for all the houses of each model is A times B. So the product of these two give us the type of material and how much we need. So A times B. A is 3 by 2, B is 2 by 3. Because these two are identical, we can multiply them. The result is a 3 by 3 matrix. So, for example, the first entry, I'm not going to do all of them. It takes some time. But if I multiply these two, 0 times 10, 30 times 50, I get 1500. That's my very first entry. Okay. If I multiply this one by this, 10 times 10, 120 times 50, 1000. They add up to 1100 is the second one. I'm talking about the first column. 20 times 10, 200, 20 times 50, 1000. They add up to 1200. So we have 1500, 1100, 1200. And now go with the next one and the next one and the next one. This is, my apologies, 2 by 4. This is 2 by 4. So the result will be a 3 by 4 matrix. 3 by 4 matrix. So just for the sake of argument, this one, okay, I multiplied now by the next one, and the next one, and the next one, and the next one, okay? And so when we do that, it results in the following class. Again, let me just erase my word so I can show you what we just discussed. If you look at this one, 0 times 10, 30 times 50 is the first one we entered. And 10 times 10, 20 times 50 is 1100. This one. This one is this one. And let me use a different color. This one is this one. So that results in the first column. Now, if we work with this one, gives us the next one, and the next one, and the next one. What does it mean? So we have multiplied A by B. A represents the models, B represents the type of material. So that means now model X requires 1500 concrete units of concrete, 30 units of lumber, 600 units of bricks, 60 units of shingle. So as an example, let me just box that so you see what I'm talking about. This one means what I just mentioned. What about the second model Y? That needs 1100 units of concrete, 40 units of lumber, 400 units of bricks, 60 units of shingle. That's the idea. And now we can figure out the cost by multiplying by the cost here per unit of those. In other words, total cost per model is AB times C. Multiplying the result here, the total amount of material, matrix AB, and the cost, matrix C, gives the total cost of material. So let's multiply. And notice what we have here. First, the dimensions. This is a 3 by 4. This is 4 by 1. And because this is 4 and this is 4, we can multiply them and the result will be 3 by 1. So for example, we multiply this one by this. Okay. 1500 times 20, 30 times 180, 600 times 60, 60 times 25, and it gives us the first one. So this one is the product of 1520, 30 and 180, 660, 60 and 60, and 25. Add them up. Now, if you multiply this one by this one, gives you the second one. And this one by this one gives you the 30, the last one, which means Model X is going to cost $72,900. Model Y $54,700. Model Z, $60,800. So that's the total cost of materials. How much of each of the 4 kinds of material must be ordered? Amount of each material needed for all houses of each model, AB. That's what we want. For the material, we said concrete, AB said model X needs this much, model Y, model Z. So if you want the concrete, just add them up. So add those numbers. This is how many concretes we need for the entire project. Lumber, 30, 40, 60. Add them up, 130. Bricks, 600, 400, 400, 1400 total. Shingles, 60, 60, 80. This is what we need. So add up each column. So these 3,800, 130, 1400, 200. So add up each column. So the total amount for each case is found in this manner. Now, we want to find the total cost of the materials, amount of each material needed for all the houses of each model is AB. Okay. D is the amount of concrete, 3,800. Lumber is 130. Brick is 1,400. Shingles is 200. Okay. So we have a couple of ways of doing that. We're going to show both ways. One is to multiply D by C. Or add them up. If we add them up, this is the fastest way. We already have this cost. This was the cost for model X, cost for model Y, cost for model Z. Just add them up, you're done. But if you didn't have that, and you had the D times C, will do the job. Which means 3,800 times 20 plus 130 times 180 plus 1,400 times 60 plus 200 times 25. And if you put them together, you get the same answer. So 2 ways, add up those that are found in the very first part, or multiply D by C, and you have the answer. All right, the last thing I want to mention is the identity matrix. For an n by n square matrix, the enter is located in row I, column I, where I is between 1 and n are called the diagonal entries, and n by n square matrix whose diagonal entries are ones, while all other entries is called zeros, is called an identity matrix I of I sub n. That means the dimension is n by n. So I2 diagonal is 1, the rest of them 0. I sub 3 diagonal is 1, the rest of them 0. Okay. That's called an identity matrix. Now we are given a couple of matrices, A and B, and we want to find A times I sub 3, I sub 2 times A, B times I sub 2. So what happens if you multiply these two? Just as an example, if you multiply this one by this one, you get 3 and the rest of them is 0. So the very first entry is 3, just in case. And if you multiply the second entry by that column, you get 0 times 1, 4 times 0, negative 1 times 0, and the first column is 3, 0. If you continue with the rest of them, you will end up with A. This will give you A, and you can try it. What about this one? So if you look at this one, for example, you get 1 times 3, 0 times 0 is 3. If you do this one, you go 0 times 3, 1 times 0 is 0. So clearly, you continue with the rest of it, and you get the A matrix. What is B times I2? I2, we mean a 2 by 2 matrix, which is an identity matrix. So if you multiply these two, you get 2 times 1, 4 times 0, which is 2. You multiply this two, you get negative 1 times 1, 3 times 0, which is negative 1. If you multiply this one, you get negative 3 times 1, which is negative 3, 1 times 0. So you get negative 3. So the first column is the same as the first column for the B. And if you continue, you get the B matrix. So what does it mean? Identity property. If A is an M by N matrix, then I sub M. If you're multiplying it from the left side, it has to be M by M is equal to N. And if you're multiplying from the right side, AI sub N equals A. If A is an N by N square matrix, then AIN or INA makes no difference. When you multiply by an identity matrix, if it's a proper size, depending upon whether you multiply from the left or right, you get to the same answer. That's the identity property of multiplication of 1 by any number. You get the same number. It's the same concept here.